Hey fellow YouTubers, how's it going? Well, I want to do a video, probably do a series of videos. I want to talk about fake gold and fake silver and silver testing methods. And I really want everyone's input. Uh, this is a device I sort of invented that I'm going to show a bit later on. What I want to do in this video is talk about specifically, how we test. This is a piece of tungsten, right? I got a whole bunch of coins, and this is a same size piece of gold. Has the little AU on it that I got from a company. In essence, to show you just how much testing I've done, I got lots of little, I'll show you all the coins I got. These are just different metals. I got, lead, niobium, zirconium, bismuth, tin. I know you can't see the details. The key metals that we're all worried about is, copper. I'll show you aluminum, silver, tungsten, and gold. Right? So these are metals I've been using. Why? Because they're cheap metals. If you're going to make fake things, obviously, you need to use metals that are cheaper than the actual product. And coat it with the product, hopefully. What I want to do first is just talk about the methods and then show you my device and how hopefully it's something that I can sell or make in the future. So here I made a list I've been researching this for many years. Now the testing methods that you see, the only ones that I know of. Please tell me if you know of any others. Of course, there's the acid tests, and the assaying is the most definitive one. But these two are destructive methods. Acids are, of course, great for you jewelry types, cash for gold people. But it's not something we want to do to our, nice coins we buy to test them. And assaying, of course, it's not something you're going to do regularly, go to the store and get an assay. So those are something we don't do very often, unless you know it's fake. Density. So as far as checking density, that's something we should all know. We all know the density of gold. What do you need to check density? Well, I always suggest just getting gold coins, right? And as long as you know the size, you make sure you got your scale to measure the weight, of course. And the other thing you want is a set of calipers, right? Now you don't need to buy a fish, one of those fish devices. As long as you know, this is a gold maple, right? And I know gold maples, the dimensions are 30 millimeters, right, in diameter. So I got 30.05. And the thickness is, of course, 2.8. Right on. So as long as you know you got a coin that's in the proper thickness that the mint gives you. I mean, the only things that are denser than gold are more expensive than gold or radioactive. So let me show you another thing, though. I have a gold. This is a platinum maple right here. Now, in terms of sizing, they're the exact same diameter, but the density, right? Platinum is what did I write? I calculated that platinum is about 9% denser than gold, right? When you look at it, look at the thickness of them. The only difference, the diameter is the same, but what's the thickness? The gold you saw was 2.8. And according to the mint site, the thickness of a platinum maple, 1 ounce maple, is 2.6. So here it is, 2.62. So this is why you need one of these. Right? You can tell, just to give you an idea, if you need to do a quick, easy way to back to test the difference because it's hard to see with the eye. If you have a gold maple here, if I put a flat bar across the top of that maple and I slide the platinum under, it'll go right under. But if I try the other way around, right, obviously I have the bar across the platinum now, and I try to slide the gold under, it won't. So it's that 0.2 millimeter thickness difference on there. It's hard to tell. And the reason I wanted to show you this, some of you may not have seen a platinum 1 ounce compared to a gold 1 ounce. And I used to think, oh, you know, platinum's 21 grams per cubic centimeter and gold is 19. But the difference is very minimal. So there we go. And the difference between copper and silver, right? Silver is 18% denser than copper. Although silver and molybdenum, which we'll see later on, they're pretty darn close. They're even you know, just a few percentage points. So scale, the caliper, right? You want to know what the density is. There is other ways using water and all that stuff, but those are just, anyways, look it up yourself. There's the ping test. That's only really relative for silver. Gold doesn't really ping. There is the magnet test that you can use to find out if there's iron, or there's about 10 metallic elements in the periodic table. So it'll eliminate all of those. Now talk about the electronic gold testers. What do? You've seen them, you know, they test to see what the percentage of gold, right, is in the jewelry. And they're basically just checking electrical conduction through the metal. So it doesn't necessarily check if you know, one of these is inside the, you know, plated gold. It's good for checking the carat of the, right, 10 to 24 carat. And of course you have to, you know, it's a bit annoying to lug around. The other one is ultrasound, is very good too. That's a great thing for these, by the way, when you're talking about bigger sizes. So sound travels through the tungsten much better than the gold. Right. The thing is, these are small coins, so you know it might tell you the difference. Just we're only talking like 2-3 millimeters. By the way, this is the coins I got from the place I got it from is this is a 8 gram, and so ultrasound is great, but once again expensive, and you have to use gels and all that. And then there's the XRF machines, which wouldn't even really bother to talk about, because they're thousands of dollars. Plus, they only do the surface, right? Unless you got a hospital X-ray machine that goes straight through. The XRF machines just bounce off the surface of a coin, so they don't go through the thickness. So I want to know, you know, what if I got one of these? What if I sold you one of these at the store or whatever, and it was just plated with many thicknesses of this gold? How can you tell? Well, this is where I came up. I've been studying this for quite a while. If you go to periodicelements.com, periodictable.com, you can find anything you need to know about the elements in the periodic table are on that site. And this gives you an example here. I'll show you the numbers later on, but look it up yourself. But this shows you the electrical conductivity of all the elements in the periodic table. And you notice there's a handful up here. This is copper, silver up at the top. You got gold, aluminum. You got a few, I'll skip the elements that are not relevant, like calcium and sodium. But you got magnesium down here in the corner here. Magnesium, tungsten, molybdenum, and then everything else here is sort of for our purposes, not doesn't conduct electricity for my needs with this machine. So just to give you a numerical value of what the conductivity of these different metals are is this. So the electrical conductivity, according to that table, is in 10 to the 7 Siemens per meter. It's just a measure of how the conductivity of it. You could look up Siemens per meter. That's your homework. Anyways, silver and copper are basically have the same conductivity, right, for our analytical purposes. Right? They both have 6 times 10 to the 7 Siemens per meter. Gold and aluminum are 4 Siemens per meter. So you notice it goes down by a factor of 2 there. And the other interesting elements, magnesium, molybdenum, and tungsten, or wolfram, are 2 Siemens per meter. So because I want to talk more about the gold and tungsten here, so essentially gold is 2 times as conductive as tungsten, right? So electricity will travel twice as fast through the gold compared to tungsten. And so that's where this comes in. Because the gold travels, right, twice as fast, or the electrons travel twice as fast, right? Electrons travel twice as fast through here as they do through here. I wanted to make a device that that can measure, give you an idea if it might be fake tungsten or gold in there. So all this is I can show you. This is just a channel. It's an electromagnetic channel. That's basically just the size. I made this one just the size for these, right, little coins. And basically it drops straight down to the bottom here. And as it passes through that electromagnetic column here, it'll time how long it takes. And you'll see how relevant this data is. So the channel in here is like the magnetic strength of an MRI. Super strong magnetic field. So what I want to show you is just show you quickly. It's just basically you turn it on and it's got I put infrared detectors that time it. And every time you do it, you just have to reset it. Right? So let me just start off by dropping the gold down here. So when I drop the gold in here, it comes up, comes out the bottom. Gold takes 1.09 seconds. So if I drop it many times, I'll just show you it goes within a range, obviously. It's usually around 1 second. 1.1, 1.07, 1.09. So the gold I calculated, usually takes about 1 second. The tungsten, pure tungsten, how long does it take? 0.32, 0.35, 0.31. So tungsten, like I've measured many times, can say it goes down in 0.4 seconds. So here's the stats. I've done lots of drops, obviously, with all the different elements I have. But gold, 1 second to drop through. Tungsten, 0.4 seconds. Now, as we know, gold and tungsten are the exact same density. So density-wise, weight-wise, they're the same. Actually, this one in this coin, because this one's not stamped, it's a bit heavier than the gold, which is why it drops faster. But you notice, since gold is twice as better of a conductor of electricity, it takes twice as long to drop. So if you had something that was 50% gold and 50% silver, and I sort of tested this by tying, testing different metals, this thing I can't drop it, it'll get stuck, but this thing will be in the range between 0.4 and 1 second. So it's not exact evidence, but it gives you sort of an idea of whether this might be fake or real. Let me drop the other, give you other statistics here. Let's drop the silver down there. Silver takes 2.7. So on average, I found silver takes 2.7 seconds to drop down here. Copper. So remember, copper is 18% less dense, right? So lighter than silver. So how long is it going to take? The copper takes 3.12. So copper, I found, just usually takes about 3.1 seconds to drop. So do the math. The copper is actually, this copper is 15% slower, right? And it's approximately 18% less dense, right? So it gives you sort of an idea that this thing differentiates the density. The other interesting one is when I compare gold and aluminum, just to tell you how fairly accurate this can be. Aluminum and gold are the exact same, pretty much the exact same electrical conductivity, right? But gold is approximately 7 times as dense as aluminum, obviously, right? 19 grams versus 2.7 grams. Once again, gold takes how long? Right, 1 second. So if this is 1/7 the weight of gold, how long is it going to take to go down? Approximately. Okay. 6.2. So it takes 6 times as long, right? Obviously, this isn't exact measurements, but it gives you an idea that when it drops through this channel, and this isn't empirical evidence, this is just comparison. So I know it's a long video, but this is a device that I'll do more videos out, maybe try and make them shorter, but I wanted people's input on what they think about this. It's simple. It's something I'd like to make different sizes and sell them out to you guys. And it's a good way, I think, of testing different elements, especially to find out if, you got a gold-plated tungsten coin, right? It's just going to drop straight through here. Thanks a lot. Talk to you later.